So it's our pleasure to host today Julien Favier. Sorry for the pronunciation. He's a professor in fluid mechanics at Aix-Marseille University, expert in numerical modeling of fluid structure interactions, applied to aeronautical and biological flows. He did a PhD in Toulouse on experimental aerodynamics, I would say. And then he moved to two postdoctoral positions in Genova and here in Madrid at CIEMAT. And finally in 2012, so 12 years ago, he moved to his current university as assistant professor and has been promoted to associate and full professor. Now, currently, he is the director of M2P2 Lab, which has some meaning in French that he will tell you, with more than 100 people and 40 permanent researchers. And since January this year, 2024, he's coordinating a European project called Falcon, in which, among others partners, he's collaborating with Airbus Spain on fluid structure interaction, analyzing noise, aeronautical noise, and other topics that I'm sure he's going to be talking about. So, Julian, thanks for being here today. Floor is yours. I think you can talk on this one.
Thank you very much for the presentation. Can you hear me? Yes, perfectly. Okay. Ok, antes de empezar, algunas palabras en español, porque solo para decir que me hace mucha ilusión estar aquí hoy hablando de mi investigación, porque pasé 4 años de mi vida en Madrid y tengo muy buenos recuerdos de este tiempo, y está, pues me hace mucha ilusión. Pues ahora cambiamos al inglés. So I will talk about free structure interaction in aeronautics, and I didn't know where to put the focus on my presentation, so I decided to put a bit more focus on lattice Boltzmann method for many reasons that I will present after. So M2P2 Lab stands for mécanique, modélisation et procédés propres. Basically, this is numerical simulation in mechanics and process engineering. So where is the pointer? Okay. So Marseille is here in France, so it's South France, and the M2P2 belongs to Aix-Marseille University, CNRS, which is the French National Center, and Central Mediterranean, it's an engineering school. So there are 40 researchers. We have 8 PIs working in aeronautics, and we are very focused on lattice Boltzmann method. We can say that it's the first lab in France for that method. We are a member of the Institute of Mechanics and Engineering. It's the second center in France in mechanical engineering, and we do very large applications, not only aeronautics, but also biomedical, combustion, fusion, plasma fusion, urban flows, and process engineering, like chemical reaction. So today I will focus on recent developments in free structure interaction, FSI, using lattice Boltzmann and immerse boundary. The positioning of my research and my lab in France is to target realistic applications. So for aeronautics, it means high Reynolds number flows, high Mach flows, and large deformations and high vibrations. So this is a challenge, and the idea is to push forward the capability of the numerical simulations to target these applications. So when building this information, I liked a lot, when building this presentation, I was thinking about these graphics. I will present many ingredients in numerics, and my presentation will explain how to put them together to target this objective. So I will first talk about the challenge in terms of physics that are posed by this objective. Then I will do a part on how lattice Boltzmann works, intentionally a bit pedagogic, but it's not an easy task to put it in a small presentation, but at least I've tried. You will tell me what you think. Then how to couple discrete solver to solid dynamics. Mainly this is where immerse boundary is. And then fourth part is how to upscale the available methods to target compressible and high Reynolds number flows, and some results and ongoing works on FSI. So challenge in terms of physics in 2 words, it's moving boundaries in high Reynolds and high Mach number flows. The target is the configurations that are inside the Falcon project. So it's a European project that I am coordinating. It involves several academic centers and industries in Europe. So for Airbus, there are 4 countries, including Spain, that I will visit tomorrow. You have, as a partner, MSC Software, who is commercializing the FEM solver, finite element solver. Here there is Karlsruhe University, who is developing OpenLB, open source lattice Boltzmann code. This is DLR, the German Aerospace Center for Experiments. And so Aix-Marseille University is here, and we are in charge of one code, which is ProLB, that I will present just after. The configurations we target is the deflection of a wing, a high aspect ratio wing, so much thinner and much larger. The vibration of a seal here that can flap in a 3-element airfoil, so it's a high lift device, and in the middle of the 2 elements you have a seal that ensure impermeability and that will flap. It produces noise inside the cavity, so this is what we will address. And this is the 3rd test case. It's a carbon seal noise, so it's a seal between the fuselage and the wing that vibrates at a very high frequency and that produce a very characteristic sound in the cabin that we want to control, we want to mitigate, we want to understand the physics. The physics is linked to an instability between the pressure, the inner pressure, and the pressure on the upper side of the airfoil. And this is what we are targeting. So this is quite challenging test cases. Again, in the European projects, so there are different work packages. So this one is numerics, this one is experiments, this one is boost is about HPC, and this one optimize. I'm just saying it because what we do here is we use surrogate models based on neural networks and AI to produce low-cost estimation, low-cost approximations of the phenomenon that I've shown to replace the high-fidelity simulations with the target of controlling the noise. So we use two solvers for the fluid, ProLB, which is the one we developed in Marseille, and OpenLB, which is an open source one. And for structure, we use Nastran and Espresso, 2 solvers. We also have a task on building a monolithic approach for FSI, which means solving fluid and solid equation within one set of equation at one time. Okay, so in terms of physics, so we use and tools. So we use this code, which is called ProLB. It's a mixed academic and industrial code in France. So it's co-owned by Aix-Marseille University, Central Lyon, two universities in France, Airbus, Renault, the car manufacturer, Safran, and CS, who is commercializing the software. So it's a licensed software, but it's used freely in the academic center for research. Basically, in LBM at the lab, we are 4 PI working fully in LBM. And basically, so we have here an area which is about reactive, compressive, and multi-phase flows. Here, which is dealt with Pierre Boivin. He was also working at CMAT several years ago. In turbulence aeronautics, there is Eric Serre and Pierre Sago who are dealing with this. I'm more centered on FSI and moving walls. And at the intersections between these areas, we have some interfaces that I will comment here. So mainly today I will focus on these interfaces. Okay. So apart from Falcon, we have some other research projects that are funded by here. This is the National French Agency, which is funding this project on the use of lattice Boltzmann methods for aeronautic applications. And so it's a thermal application, moving walls. So in that part, I'm involved in this work package, but also multi-species and reactive flows and multi-phase. And this one also is, I won't get into detail, but it's also applied to aeronautics. So, which is why we have a lot of activities on this method. So, lattice Boltzmann methods, how does it work? So here are some keywords about this that summarize the slides that follows. So it's a mesoscopic approach. It's the first difference with Navier-Stokes solver. It's based on the Boltzmann equation, so not Navier-Stokes equation, but there is a formal development that can formally shows that you can recover Navier-Stokes equation starting from lattice Boltzmann equation. And we'll talk about discretization and streaming and collide, which are very special features of LBM. So the slides that are following are a bit heavy in terms of equations, so I won't comment everything. So feel free after to, if you have questions, to come back to me. But I will try to be as synthetic and as pedagogic as possible. So how does it work? So it's a mesoscopic description. What does it mean? Is that it's closer to the particles. So it's still continuum mechanics, but closer to the particle. So which means if you come back to what is a fluid, so it's molecules interacting together and colliding. So it's closer to that description of the flow. It's linked to the kinetic theory of gases, and which is why it's based on Boltzmann equation. The good thing is that the good thing or the bad thing, depending on how you see it, is that it's built on a Cartesian grid lattice. So the industrials liked it a lot because it's very easy to mesh complex geometries. And for me, it's interesting because it fits very well with the immerse boundary. It fits very well with the Cartesian grid. It's easy to code also. And also it's suitable for massive parallelization because the non-linearity is local. So there is this citation from Suchi, who is a scientist who's been working in lattice Boltzmann. The non-linearity is local. So this means that the heavy part of the algorithm can be dealt locally on one cell, which is very, very nice for parallelization. And non-locality is linear. This is just made for the citation, which means that you will see that there is an exact streaming of the f, the function distribution function, which gives very good properties of the algorithm. This is an illustration on taken from the industry of the high-speed French train TGV. In lattice Boltzmann, it's very easy to mesh complex geometries like the full train, taking into account all the details for an engineer working there. With respect to doing a body conformal mesh, it can take weeks or months even. In that case, it's done in 30 minutes, so which is why there is a big success in the industry for this technique. But it's not only about performance, it's also about physics. This is what I'm showing here. So it's second order in time and space. So it's not a high order method compared to high order Navier-Stokes, but it has some very good dispersion and dissipative properties, very low errors. So if you compare it with high order Navier-Stokes solver, it behaves very good. And this very low dissipative properties, very interesting. And it's because of the intrinsic nature of lattice Boltzmann closer to the particle dynamics. In this story, PowerFlow, which is a commercial lattice Boltzmann code, it started in 2007 at PSA, which is Peugeot, the car manufacturer, doing some free computations, like to the company, offering them free simulations just to show them what they are doing. And now they claim to have more than 90% of the market, which means that it's widely used by industry. In France now, car aerodynamics are only using lattice Boltzmann. They are not using the Navier-Stokes solver anymore. Okay, so how does it work? So it's based on this equation. So it's an equation of transport for F. F is a distribution function, is the probability of finding a particle at a given point in space, at a given time, and for a given velocity. So here, this is the space, x. Psi is the discrete velocity, which means a particle can have any velocities and time. So there are 7 unknowns, and so the left is just a transport equation, except that here you have the spatial terms, and here you have an A black psi, which is the gradient in the space of velocity, which is confusing when you come from Navier-Stokes framework. Seeing this appearing is a bit confusing, but you will see it. We will get rid of this quickly. And on the right is the collision term. Basically, it tells you how the F, the distribution functions are evolving and how they collide together. Okay, so the second term is for interparticular collisions, but it can be very simplified. By this formula saying that you have 1 over tau here, it's like a relaxation time, and the F's are relaxing towards an equilibrium state. So this comes from the central limit theorem. So for large numbers, you have any distributions that tends to the Maxwell distribution equilibrium, which is a function of the velocity, of the temperature, of the density, etc. So this is where the kinetic theory of gas is. And this model was proposed in 1954, and it's still widely used. So now we used more sophisticated methods for these collision models, but it works very fine. And it has to respect some collision invariance to conserve the mass and the momentum. Okay, so how do we get rid of this psi? So by integrating in the space of velocity. If you, So if you integrate here the F over the space of velocity, you recover the macroscopic quantity, which is rho, the density. Here, if you integrate psi f, you recover rho u, and same for energy. Here, this is the internal energy. So basically, this is a link between microscopic and macroscopic equations. Like temperature is the macroscopic representation of the molecular agitation. So it's linked with psi square. So this is how you pass basically from the scale microscopic to the macroscopic one. And so it's not a molecular, lattice Boltzmann is not a molecular code. It's closer to Navier-Stokes in the sense that for time and space, you have continuum mechanics. It's just that with the discrete velocity, it takes into account the possible velocities that a particle can have. Okay, sorry. Don't be afraid. Okay, tack. So basically, to pass from Boltzmann equation to lattice Boltzmann equation, we need to discretize. Lattice, it means a Cartesian grid. So what do we need to discretize? First, the space of discrete velocities, all the velocities that can take a particle. So it's in 3D, so it can be whatever value in 3D. And we need to discretize space and time like every Navier-Stokes solver. So I would focus mainly on the velocity space because for space and time, it's a Crank-Nicolson scheme, nothing really original. But for the velocity space, it's something a bit new. The idea is to use Hermite polynomials and Gaussian Hermite quadrature. I will show you why. So the first thing is that is to project the distribution functions on a truncated basis of polynomials. So it's done in a lot of applications. In that case, why do we use Hermite polynomials? Is that it fits very well with lattice Boltzmann. Sometimes we wonder, like, I had this feeling many times, like if a mathematical object was invented for physics, or if it existed long before. So in every time the answer is the same, it existed long before. But in that case, you have really the feeling that Hermite polynomials were invented for lattice Boltzmann. I will tell you why. So basically, if you replace df's by a truncated sum of a are the coefficients and h are the Hermite polynomials, this is just the way you write the expansion. So a, by definition, is the integral of hf. So let's see what are Hermite polynomials. So if you go and see their definition, so omega of psi is an exponential minus psi square. And they have this formula. So basically, when you take, this is for n equals 0, you put n equals 0 here, you have a derivative of order 0. And then if you take the order 1, you derivate this one time. So you have 1 here for the polynomial of order 0, psi here, psi, etc. You have these expressions. And when you compute the a here, the integral of this, you recover exactly the macroscopic variables. Rho u, p, which is the stress, so in lattice Boltzmann, they call it the pressure tensor, which is, in fact, is the pressure and the viscous term together in a tensor. This is the tensor, internal energy tensor flux, etc. So there is the link between the mathematical expansion in Hermite polynomials and the physics, which is very, very useful and also very nice here. And then once you have this integral, you need to approximate them numerically. How do you approximate an integral? You can use a rectangle rule, you can use midpoint rules, or in that case, again, you can use the Gauss-Hermite quadrature. It's like made for functions that are that have these shapes: exponential minus x squared times f. So they have these definitions. Here you have wi, which is the weight of the quadrature, and this is the function evaluated on the point xi. Okay, this is a classical quadrature, except that is the Gauss-Hermite one. Basically, if you reformulate a bit this expansion, f over omega is a polynomial of degree less than n. H is a polynomial of degree less than n. So at the end, if you call it R, it's a polynomial of degree less than 2n. So the A here can be reformulated into a sum where you have a polynomial of degree less than 2n. Why is it important? Because Gauss-Hermite quadrature gives you an exact approximation of the integral for a polynomial degree less than n if you use a sufficient number of points in the quadrature. So this is very important, and this is one of the reasons why it's so efficient, the method, is that it's not a numerical approximation of the integral. You have the exact approximation of the integral if you use a sufficiently number of points in the quadrature. So basically, you replace dA by a sum of wi, which are the weights of the quadrature. This comes from maths, and this is the function evaluated at psi I for given discrete velocities. This is the quadrature points. So as a recap, we project the distribution function on a truncated Hermite polynomial basis. So basically, we approximate the function as polynomials, and then we compute these polynomials. We evaluate them numerically thanks to Gauss-Hermite quadrature. So it's a kind of optimal sampling of the velocity space. You start for one point in space. Imagine you come back to Navier-Stokes framework. From one point in space, you have an infinite number of possible velocities. In that case, you reduce it to n number of quadrature points, and you will see that depending on if it's 2D or 3D, you have more points. So this is the last key feature. So this is, you do for the A, for the F equilibrium, you know, the right-hand side part, you do this expansion and you end up with this expression here. You just apply this sum and you obtain here the order 0, order 1, order 2, and then order 3 and 4. I haven't written it, but you can find this in papers, and this is where it comes from. And so this is in 2D, you have the so-called D2Q9 lattice. D is the dimension, Q is the number of discrete velocities that comes from the quadrature points. Okay, you have, it's like if you would say on given point of my lattice, the particle is constrained to move only in 9 directions of the space. One is fixed here, one is here, 1, 2, 3, 4, 5, 6, 8. Okay, and for each direction, you have a weight that is associated to that. In 3D, you have 19 velocities. So I won't get into details, but you can build several lattices like this with a lot of velocities. And what is striking about lattice Boltzmann is that the more you add terms, normally, when you use if you are familiar with numerical methods, the more you add terms to the expansions, the more precise is your method. In that case, it's not precisions that you add, it's physics. Why? Because you add more, you remember the macroscopic velocities, you have more tensor of higher dimensions. If you have tensor of higher dimensions, you need more points to use them. You need more discrete velocities. So you increase the number of your lattice. In terms of computational efficiency, you want to have a very small number of discrete velocities. Imagine for 1 point, you have 29 possible velocities, so it's still huge. But if you want to increase the physics, you can with lattice Boltzmann, and then if paying the price of having a larger lattice, you can do it. So this is what is a recap in this table. So if you take up to order 4, you recover incompressible and non-thermal flow, fluid flow. So Navier-Stokes, athermal, quasi-incompressible Navier-Stokes. If you put more tensor, more terms, then you recover, so this worked for supersonic regimes in the limit of small max and small temperature variation. And if you put even more, you can recover even the Burnett equations, that are the equations for rarefied gas flow that are not relevant for today's talk, but you can get to that. And so this was the description of velocity space. For time and space, I won't detail it here, but it's a Lagrangian integration using a Crank-Nicolson scheme with a change of variables to stay explicit and second order. So explicit is it was meant for computational efficiency. And with this change of variables, you can switch from order 1 to order 2, which is also very important. So basically, you have the equation like this. This is lattice Boltzmann. So Fi, it stands from one discrete velocity of x plus xi I. So there is a delta t which is equal to 1 here. Xi delta t is the distance at which you will send your particle distribution. Delta t equals 1 because there is a special normalization in lattice Boltzmann that allows you to do that. And this is the collision term where the Fi relaxes to the equilibrium, and this is for a force term. I put it here because then we couple it to immerse boundary, so this is the force term is. And then, so you solve this at each iteration, and you recover the macroscopic variables, rho and rho u and energy, by doing what is called the macroscopic reconstruction. It's just the numerical version of the integral that I was showing before. So in practice, the LBM algorithm is split in two parts. It's called the collision and the streaming. Collision is where you apply this term, the 1 over tau Fi minus Fx is the relaxation to the equilibrium. Fx contains the nonlinearity. So you see this is local. You have x and x here. Everything happens on one point. You relax it. And then streaming, you just move the distribution to the neighbors. And with a mathematical development, which is called Chapman-Scott expansion, you can show that you recover Navier-Stokes equation from the lattice-Boltzmann equation, and you have a link between viscosity and tau. So this is where the viscous processes are inside tau. Okay, so this is a graphical view of streaming and collide. So in a typical iteration of lattice-Boltzmann, you have your Cartesian grid. On one point, you have equilibrium functions. They are function of rho, u, and theta, the temperature. So this is the distribution function. You collide them, so you change the distribution. Here it's in 2D with nine distribution functions. And then you prepare to stream. So every node will send the distribution function to the neighbors. Okay, so this comes like this. So then every point receives distributions from every direction of the space. It compute first the update of rho and rho u, and compute again the equilibrium function for the next step. So this is how it goes. So this was for basic lattice-Boltzmann. So how do we couple it for FSI? I will skip that part. Is for moving, we use overset or chimera meshes for rotating geometries. I will focus on arbitrary motion, not rotating motion. Arbitrary motion, we use immerse boundary method. So I know there are activities on that, so I will not spend too much time on basic stuff on immerse boundary, but just saying the principles is to use volume force added to the momentum equation and energy equation when it gets to compressible flow to account for the presence of the boundary. So it's based on interpolation and spreading operator. You don't have any meshes. It fits very well with Cartesian grid. And basically we are calibrating the method, computing a Lagrangian weight to ensure a mass loss which is less than 1%. And what is very interesting is that this method is very stable when solid gets into contact together from the fluid part. And this is interesting features. So these are the three operators of immerse boundary methods. You have interpolation. You see here on the nodes that are, if you take one point here, which is called a Lagrangian point, if you want to know the velocity on these points, you interpolate based on the value on the red square here by using this formula. Delta is a Dirac delta function. And so basically the algorithm is interpolating the velocity on this point, computing the force, so that you have a no-slip boundary condition based on here the velocity of the boundary, and then spreading the force. Okay. So basically the delta function in the mathematical space, so it's the Dirac delta that we all know. When it gets to the mesh, it has a thickness, and we use bell-shaped functions to take into account this delta function. So it's like saying around each Lagrangian points having an area of influence of this point. So the choice of the delta function at the end you can show doing a Taylor expansion of f if given the fact that the function is sufficiently smooth. You can show that choosing this delta function boils down to imposing some moments on the delta, some conditions on the moments of delta. And there are several ones available in the literature on that. So I won't get too much into detail on that. You can have conservations, properties for immense boundary, etc. Basically, I started when I was in Madrid, like 13 or 14 years ago, about calibrating the weight of the quadrature of this spreading operator to improve the mass conservation properties. Okay, so I won't talk about that. It's very easy to couple with lattice Boltzmann compared to Navier-Stokes solver, because you use here, this is a volume force in the macroscopic reconstruction. If you apply the interpolation operator of immerse boundary to the left and right hand side of this equation, you recover the forcing here. And you have an expression of the forcing, which is very straightforward, and you can use it in lattice Boltzmann algorithm. So basically, here you have here you solve lattice Boltzmann with the force, and you find the forcing using the formula I've just shown, and you just spread the force and compute the macroscopic velocity again. It's very straightforward to couple it with lattice Boltzmann compared to Navier-Stokes solver. Okay, so this is just a video to show it's a very a toy simulation. It's a closing of a channel with a valve, and you have the immerse boundary points that are going outside of the domain, and it shows the robustness and the stability of the methods. Like especially when the solid are getting very close together, very close to each of them, and also when they cross, the method gets very stable. Okay, so FEM, I won't talk about finite element methods, but I would just say that immerse boundary method is very convenient when you have two kind of meshes. So here, imagine you have a special kind of meshes inside the cylinder and a Cartesian mesh. You just define points on the boundary, and you just exchange forces between the domains. It's very easy. And how do we couple fluid and finite element solver together? So we wanted targeting realistic configuration. We wanted to stay at a CPU cost which is reasonable. So for this reason, implicit methods were discarded. So we want to stay explicit. So how do? We just advance in time solvers in parallel, not doing a strong coupling. So this is called a wake coupling algorithm. So basically, you have the solid which sends his position to the fluid solver, which advances in time based on this position. It sends the forces to the structure solver that advance in time, etc. So it's what we call explicit one. It's possible to improve it doing mid-step and also doing some sub-cycle, but I won't talk about this. But when the physics gets more coupled, we need to improve this explicit coupling. Okay, it doesn't work this. Okay, never mind. So this is some typical validation we did. Like this is a membrane with two cavities, one different pressure, and in the middle you have the membrane which is deforming as a function of the pressure. It's a test to measure the impermeability of the wall using immerse boundary. These are the other test cases very well known in literature. This is the one with, so it's not written here, but there is a density ratio of 1, which means it's between fluid and solid, so it's a quite coupled dynamics. It's called the Turek test case. It's a very well-known academic test case. This is a 3D flag. So we obtained very good, with this framework agreement with literature. This is a 3D flag. Also, where there are available experiments and numerical results in literature. So how do we move from that to more realistic cases? So this already worked quite well. So we use LES for lattice Boltzmann. So the way to code it, the way to impose it in lattice Boltzmann is quite straightforward. So we use two kind of models to account for the unresolved scales. So that are variants of Smagorinsky models that are written here. And it's just the way to do it is just to add a turbulent viscosity to the tau. It works. And the rest works exactly the same as Navier-Stokes solver. We use a spatial collision model that I won't detail here, but it also allows to, it's more sophisticated than the 1/tau f minus fx. It allows to have good properties in turbulent flows. We couple the immerse boundary to a wall model, okay, using a power law. Basically, we define an intermediate point here, close to the wall, where we impose the velocity that comes from a power law. Again, I won't detail more. The idea is to decompose the immerse boundary to a tangential and a normal component. So the tangential component is calculated using tau wall, and we use immerse boundary to impose it. And for the normal contribution, we use the regular immerse boundary to avoid fluid penetration. Okay, and for compressible LBM, there is a way to do it. So I was telling you, you can add more terms, more physics by adding more terms. What we do is we use lattice Boltzmann methods for the athermal physics, and we use finite difference or finite volumes for the energy equation. So it's hybrid methods that we use, LBM and finite volumes. So we've been working quite a lot on that to improve the capabilities of the LBM in compressible flows. So now we're able to tackle transonic and supersonic configuration with that. So some illustrations on the results we have on, so both for compressible and FSI, and also the challenges we are facing now, in particular within the perspective of Falcon project. So this is a 3-element airfoil, which is fixed to start with. So it's 1,000,000.7 Reynolds number with an angle of attack. The Mach is subsonic, and so we have 55 million grid points. We can the solver is able to do a mesh transition, mesh zones, and so this we were able with this configuration to recover the very well the results of in literature and also the physics with so inside the recirculating region. We have inside the cavity between the elements, there is a recirculating region here with Kelvin-Helmholtz instability that changes into harping vortices, and that creates the turbulent wake here. And so this is the baseline configuration of the test case of the Falcon project with the seal. And when we compare it to different in different sections, we have very good agreements with literature results. So this is a challenging test case because of the Reynolds and also the Mach number, which is 0.8. And also this was the first simulation using lattice Boltzmann for such realistic condition. So the Reynolds number is 11 million, and we used 64 million green points on that. On 500, if I remember correctly, around number of processors. And we were able to have very good agreements with experiments on that. This is the impact of shock on the cylinder, which is modeled by immerse boundary. So we try to push the limit towards, to push the method towards its limit, and in particular is the presence of shock. So here we monitor, to validate this, we monitor this point, which is the intersections between the wakes here. So we have good agreements with literature. This is what we see here. So this was for fixed geometries. Again, so to tell you that we have strong problems with shocks using immerse boundary. So this is what I've shown is like what we can call diffuse LBM. You see there is a delta Dirac function, so it's not local. But when the shocks are attached or too close to the wall, we have the hypothesis of smoothness of the function that is violated. So we have problems, and this is what is shown here. At the top, you have the IBM, and at the bottom, a reference simulation, not using IBM. So you see there is a discrepancy here on the presence of the shock. And so we have to use a sharp interface. We have to, we are still working on how to use IBM in that case, because sharp interface do not allow to move easily the geometry. This is the same. So this test case is quite challenging because it's Mach number of 6. So it's what we can call supersonic or hypersonic flows. And this is a diamond airfoil also where you have attached shocks where we are obliged to use sharp interface. Okay, so this is moving geometry. I don't show it. This is a simulation of a boat with imposed motion with immerse boundary it was a research project for the French government. This is a fan using a mesh transition for moving geometries in real test cases. So this was a paper from 2 or 3 years ago with the use of LES and power law in lattice Boltzmann and immerse boundary with a moving geometries. And this is the velocity profile we obtained with quite a good agreement. And I will show you this last test case. I think I'm on time. So this is the shock, which is rising on a flexible plate. So it's a very challenging simulation. So it's the first time that is done numerically, at least with lattice Boltzmann, but maybe also numerically. So here you have a flexible plate here, and the shock will get convected here, and we basically simulate the free structure interaction of it using the finite element solver, and so it's only 3 milliseconds the physical experiments. So you have Schlieren visualization here, and we are able to. So this is an ongoing work. We have good agreements with the experiments that are done in shock tubes, and this shows that the method is able to handle this kind of configuration successfully. This is a comparison with the prod. And the last thing on other things I'm doing at the lab, it's on aortic valve. So in 2 words, we can do micro CT imaging of hearts, which can be native or prosthetic valves. Here you have we have an algorithm to reconstruct the leaflets of the valve. We are able to print them in 3D. And what we do, you can imagine, after printing them, we can simulate the free structure interaction of it. There are very nice physical things to look at here, especially the flutter on the leaflets, which is very close to the one we observe in aeronautics. Okay, thank you very much.
Thank you, Julian, for your presentation. Questions? We have 10 minutes maximum for questions. Anyone in the audience? Let's start with Javi and then Mario. Okay.
Thank you very much for the presentation. It was really very nice. So I have a question. When you showed the shock wave impacting the cylinder, I could see that there were like some colors inside the cylinder. Is that the solid mechanism being resolved?
No. This is a very nice question. Okay, this comes from the immerse boundary method. So inside the cylinder, there is a flow, which is, it has a mathematical origin, but it's not physical. It has to be there to impose correctly the no-slip boundary condition, but it's very annoying in the case of supersonic regime. Why? Because you can have shocks that are generated inside the cylinder that you absolutely don't want to resolve, but you have to deal with that. Yeah, it's a very good question.
Thank you very much.
All right. Well, thanks you also for the very interesting talk. Impressive work. I was just wondering about the method. If you go to a limit that is rather collisional fluid, where you always are in local thermodynamic equilibrium, so you can describe the distribution as a Maxwellian, and that's it.
Yes.
How would the lattice Boltzmann method compare with, say, a finite volumes method in terms of accuracy, conservation properties, execution time? Would it be comparable, or would it be much more expensive, less accurate?
Okay, so it's not like a magical method. Like every method, it has some drawbacks and advantages. I would say it's an alternative to typical finite volume methods. Mm-hmm. We can say that, like, there have been like twin comparison on industrial configurations, like for airplanes. It comes that a Navier-Stokes finite volume solver needs less points than lattice Boltzmann mainly because they use body conformal mesh. Mm-hmm. But for one iteration, and also because of good parallelization properties of LBM, it's faster to compute one iteration. That's right. So okay. Depending on the configuration, now they show that, for example, in the ProLB software that I've shown, it's faster on realistic configuration. This is how it behaves. Yeah.
Okay. What about the conservation properties? So finite volumes is conservative by design. Say?
So it's order 2 in space and time, and so it's not a very precise method.
It's not bad.
But it's not bad, yeah, depending on what you want to do, it's not bad, yeah, exactly. Okay. It's very low dissipative also, and if you use it in the quasi incompressible flows, it means to have fast computation, you can have some spurious effect due to let's say pressure waves that are traveling in at the beginning of the simulations. So there is a transient when you do the simulations. This is a drawback.
Okay. Thank you.
Are there more questions? Javi has more questions. Okay. Good.
Thank you very much. If I can have a second question, yeah. So what about the free surface flows? Because I saw this very nice simulation of the boats, like the waves. Can you also say something?
No, we haven't done that. We could, there are some versions of shallow water equation applied to lattice Boltzmann, but we haven't tried it yet. But it can be done. I think that for free surface, maybe SPH methods may be more practical to use, but we haven't tested that. In that case, it's a forced motion that we use.
Thank you.
And it seems that there is not. So I think it's 2:00, so we can probably
Perfect.
close the seminar. Let's thank the speaker again.